Everyone, today I am going to read a chapter of physical chemistry from Modern's book by S.K. Kiran. The name of the chapter is Chapter 5 Thermodynamics Second, that is second law of thermodynamics. 5.01 Need for the second law of thermodynamics. First law of thermodynamics is merely the law of conservation of energy. There are several phenomena which cannot be explained by the first law. The first law is not sufficient and has certain limitations, which are discussed as follows. First law does not put restriction on the direction of the flow of heat. First law establishes the relationship between the heat absorbed and the work done by the system. It places no restriction on the source of the heat or on the direction of its flow. According to the first law of thermodynamics, it is possible to heat water using ice without any external effort. Yet, we know from experience that such a transfer of heat from lower temperature to higher temperature will not take place spontaneously. Heat is always found to flow from hotter to a colder body. Thus, first law is unable to tell the direction of the flow of heat. It only indicates that if such process occurs, then the heat gained will be exactly equal to the heat lost. Similarly, first law cannot predict whether a gas can diffuse from lower pressure to higher pressure or water can flow uphill on its own or not. This first law provides no information regarding the feasibility of the reaction. Second law of thermodynamics helps us to determine the direction in which energy is transferred. Second, first law has no criteria for spontaneity of a process. There are several natural processes which take place on their own in one direction, but they do not proceed in reverse reaction on their own. For example, water flows down the hill but cannot flow up the hill on its own. Flow of heat from warmer to colder body, expansion of gases into a vacuum, burning of fuels, etc. are some examples of processes which take place only in one particular direction. Such processes are called spontaneous processes. According to first law, it was suggested that decrease of heat content is the reason for spontaneity. This means that a reaction in which heat is evolved must be spontaneous, whereas a reaction in which heat is absorbed must be non-spontaneous. But there are some processes in which del U is positive. Still, the reaction proceeds spontaneously, such as vaporization of water at low pressure. Hence, delta U cannot be the criteria for spontaneity. Similarly, delta H cannot be used for predicting spontaneity because there are many reactions which proceed spontaneously with the positive value of delta H. For example, dissolution of NH4Cl solid in water. Thus, it is seen that function U and H derived from the first law of thermodynamics cannot be predicted the spontaneity of a reaction. Hence, there is need for second law. It is the second law of thermodynamics which defines the new state function called entropy. Thus function entropy along with other functions is used to predict whether a given process is spontaneous or non-spontaneous. 3. As stated by the first law, the exact equivalence between heat and work is not possible. First law establishes the relationship between the heat absorbed and the work done by the system. According to the first law, when heat is converted into work, the work done is equivalent to the heat absorbed. While it is seen from experience that work can be completely transformed into heat, but heat absorbed cannot be completely converted into work without leaving some change in the system or surrounding. This observation cannot be explained by the first law. The second law helps us to calculate the maximum fraction of heat that can be converted into work for a given process. Thus, the first law of thermodynamics is not sufficient and therefore an additional law which explains the above limitation is necessary. Before taking up various statements of second law of thermodynamics, we discuss what is a cyclic process and the Carnot cycle. Then various statements of second law of thermodynamics can be easily understood. 5.02 Cyclic process. In a cyclic process, a system after undergoing a series of changes returns to the original state. As shown in figure 1, a system undergoes change from state A to state B by path 1 and returns to its original state by path 2. This is a cyclic process. The net change of internal energy in cyclic process is 0, that is del U is equal to 0. Therefore, according to the first law, del U is equal to Q plus W. For cyclic process, del U is equal to 0, 0 is equal to Q plus W or Q is equal to minus W. When the cyclic process is carried out at constant temperature, the cycle is said to be an isothermal cycle. If the process is carried out in infinitely small steps, the cycle is said to be a reversible cycle. Although reversible process is only imaginary and cannot be brought into practice, but the concept is quite useful in deriving some important relationships. The most well-known cycle process is Carnot cycle. 5.03 The Carnot cycle. The Carnot cycle was named after a French engineer Sadi Carnot. He was interested in the efficiency of steam engine and other heat engines, the devices which converts heat into work. He observed the maximum conversion of heat into work is possible in a cycle like process in which all the necessary steps are taken out reversibly. Such a reversible cycle is known as Carnot cycle, and an engine operating on the basis of this hypothetical cycle is called Carnot engine. An expression for the efficiency of a Carnot engine may be derived using a schematic diagram as shown in figure 2. The system consists of a 1 mole of an ideal gas filled in a cylinder which is insulated and fitted with a frictionless piston. The gas is brought in contact with the two heat reservoirs such as T2 and sink at T1, which are maintained at constant temperature where T2 is more than T1. The Carnot cycle involves 4 reversible steps as shown in figure 2. First, isothermal expansion. Second, adiabatic expansion. Third, isothermal compression. Fourth, adiabatic compression. These processes are represented on the pressure volume diagram. Step 1. Isothermal reversible expansion. The cylinder containing 1 mole of ideal gas having volume V1 is placed on the source heat reservoir at temperature T2. The gas absorbed quantity of heat Q2 and undergoes isothermal reversible expansion of volume V2 indicated by curve AB. The work W1 by the system is given by minus W1 is equal to RT2 ln V2 by V1. As in isothermal process, del U is equal to 0, the work done is equal to the heat absorbed Q2, so that minus W1 is equal to Q2 is equal to R2 ln V2 by V1. Work done by the system is taken as negatively according to IUPAC convention. Second, step 2. Adiabatic expansion. The cylinder is removed from the source and kept on insulating base. The gas is allowed to expand adiabatically from volume V2 to V3. In this step, the temperature decreases to T1, the temperature of the sink. This path is shown by curve BC in figure 3. The heat absorbed by the system is 0 as expansion takes place under adiabatic conditions. The work done W2 is given by minus W2 is equal to CV T1 minus T2. So, minus W2 is equal to minus CV T2 minus T1. CV is the heat capacity of ideal gas. Work done is negatively by the usual convention. Step 3. Isothermal compression. This path is shown along the curve CD in figure 3. In this step, the cylinder is removed from insulating base and is kept in contact with the sink at temperature T1. The gas is compressed isothermally till the volume decreases from V3 to V4. The work done on the system is positively by convention and is given by W3 is equal to RT1 ln V4 by V3. An amount of heat Q1 having negative sign exactly equal to W3 will be returned to the sink. Thus we can write minus Q1 is equal to W3 is equal to RT1 ln V4 by V1. Step 4. Adiabatic compression. In this step, the cylinder is removed from the sink and placed on the insulating base. The gas is compressed adiabatically along with the curve dA. The volume reduces from V4 to V1 and the temperature of the gas rises from T1 to T2. The work done is positive by convention and is given by W is equal to CV T2 minus T1. As a result of these 4 operations, the system returns to its original state and a reversible cycle is completed. The total work is given by W in the cycle. It is given by W is equal to minus W1 minus W2 plus W3 plus W4. So at last, W is equal to RT2 ln V2 by V1 plus RT1 ln V4 by V1. Net heat absorbed Q is given by Q is equal to Q2 minus Q1, that is RT2 ln V2 by V1 plus RT1 ln V4 by V1. Since point T2 V2 and T1 V3 lie on the same adiabatic curve BC and T2 V1 and T1 V4 lie on another adiabatic curve AD, then using expression T V raised to power gamma minus 1 is equal to constant, we can write V4 by V3 is equal to V1 by V2. Substituting this in the equation, we get W is equal to RT2 minus T1 ln V2 by V1. From the above derivation, it is observed that the work done in Carnot cycle is in the process work involved in the isothermal operations, because the work done in the adiabatic operations cancel each other. 5.04 Efficiency of Carnot cycle and Carnot theorem. The efficiency of Carnot cycle or heat engine is defined as the ratio of work done by the system to the amount of heat absorbed at higher temperatures. Efficiency is equal to W by Q2. Or we can write that efficiency is equal to T2 minus T1 by T2. From equation, it is clear that the efficiency of reversible heat engine depends only upon the temperatures of the source and the sink, and is independent of the temperatures of the working substance. In other words, all reversible heat engines working between the same two temperatures have the same efficiency. Also, the efficiency of a reversible heat engine is maximum for the given temperatures. This is called Carnot theorem. Thus, the efficiency of a heat engine operating in Carnot cycle depends only on two temperatures at which the engine operates. The greater the difference between T2 and T1, greater is the efficiency. For a cyclic process, net heat absorbed is equal to net work done. Q2 minus Q1 is equal to W. So from here, we can find that efficiency is equal to Q2 minus Q1 by Q2. Two important conclusions arises from this equation. First, if T1 is equal to T2, then no work is done in Carnot cycle. There is more clear from equation 10, where T1 is equal to T2, then the work done in isothermal expansion at the temperature T2 will cancel out the work done by the system in isothermal expansion at temperature T1. In other words, the Carnot cycle, no heat will be converted into work if only isothermal expansion and compression will be carried out. Third, or second, it follows from equation 15 that efficiency of Carnot cycle will be unity if T1 is equal to 0. As T1 can never be 0, therefore T2 minus T1 by T1 is always less than unity. Hence, the efficiency of the heat engine is always less than unity. Thus, only a fraction of heat absorbed at a higher temperature can be converted into work. 5.05 Statements of the second law of thermodynamics. Having discussed the cyclic process of heat engine, we can now give the statements of the second law, which can be easily understood from the efficiency of the Carnot cycle. First, Kelvin statement. Since T2 minus T1 by T1 is less than 1, it follows that W is less than Q2, that is, work done is less than the heat absorbed. This means that the only part of the heat absorbed by the system at the higher temperature T2 is converted into work. The rest of the heat Q1 is given out by the system to the surrounding when it is at the lower temperature T1. Based on the observations of Kelvin, stated that the second law of the thermodynamics as follows. It is impossible to use a cyclic process to transfer heat from a reservoir to convert it into work without at the same time transferring it from hotter to a colder body. It can also be stated as it is impossible to convert heat completely into work without leaving some effects in the system or the surrounding. Although the second law has been stated in a number of ways, but all the statements have the same fundamental concept, that is, work can always be converted into heat, but the conversion of heat into work does not take place under all conditions. Second, Kelvin-Planck statement. We have seen that the work done by a heat engine operating in cycle is zero when the two temperatures are same. The Kelvin-Planck statements of the second law is, it is impossible for a system operating in a cycle and connected to a single heat reservoir to produce a positive amount of work in the surrounding. In other words, it is impossible to construct a perpetual machine which operates solely by removal of heat from a thermal reservoir. 3. Clausius statement. The heat engine operating in cycles can perform work only by absorbing heat from a reservoir at a high temperature and by rejecting the differences between heat absorbed and the work done by the system engine to another reservoir at low temperature. On this fact, the Clausius statement of the second law is based. Clausius statement of the second law of thermodynamics is, it is impossible to construct a machine that is able to transfer heat by cyclic process from colder to a hotter body without use of an external agency. 5.06 Thermodynamic scale of temperature. We are familiar with the construction of most commonly used thermometer containing mercury sealed in a glass bulb connected to a capillary tube. On the tube, 0 is the read at the length of mercury column it is contact in ice, and 100 corresponds to the length of mercury column in boiling water. The length of mercury column between 0 to 100 is divided into 100 equal divisions. Each division is equal to 1 degree Celsius. This is Celsius scale of temperature. As this scale is based on coefficient of expansion of liquid, therefore using different liquids in the thermometer will show different values of temperature for the same object. This problem got solved by the study of properties of gases. It was found that an ideal gas ceases to exist at temperature of minus 273.15 degrees Celsius. This temperature was called absolute zero. The temperature scale suggested on the basis O is called ideal gas temperature scale and is found to be independent of the nature of gas. Lord Kelvin developed a thermodynamic scale of temperature based on the fact that the efficiency of the reversible heat engine is dependent on the nature of the gas taken in the heat engine. This scale is found to be identical with the ideal gas temperature scale. Consider a reversible heat engine operating between two constant temperature heat reservoirs. One of the reservoirs acts as a source and the other acts as the sink. The temperature of each reservoir on the new scale may be taken as proportional to the quantity of heat absorbed. Q2 from the source or heat lost Q1 to the sink. Let theta1 and theta2 represent the temperature of sink and source respectively. Then on the thermodynamical scale, we can write Q2 by Q1 is equal to theta2 by theta1. This equation defines the efficiency of a reversible heat engine in terms of Kelvin temperature. By putting theta1 is equal to 0, that is 0 of the new scale, we get Q2 by Q1, Q2 minus Q1 by Q2 is equal to W by Q2 is equal to 1. Therefore, the 0 on the Kelvin scale is the temperature of the sink of the reversible heat engine having efficiency equal to 1, which means that such a cycle completely converts heat into work. It is possible only if the lower temperature theta1 is equal to an absolute 0 on the ideal gas temperature scale. In fact, the ideal gas scale and Kelvin scale are identical provided the gas is ideal. The temperature on the thermodynamic scale are expressed in terms of degree kelvins, represented as K. Further, it has been found that if theta1 is equal to 273.16 Kelvin, the triple point of water, then Kelvin and Celsius scale become identical. That is 273.16 Kelvin is equal to 0 degrees Celsius. 5.07 Entropy. The function entropy was established from the work of Carnot. Clausius in 1850 introduced the function of state, that is S, for the reversible Carnot cycle operating between temperatures T2 and T1. The efficiency is given by Q2 minus Q1 is by Q2 is equal to T2 minus T1 by T2, where Q2 is the heat absorbed isothermally at temperature T2 and Q1 is the heat lost isothermally at temperature T1. Rewriting the equation, we get that Q1 by T1 is equal to Q2 by T2. In general form, equation 2 may be written as Q reversible by T is equal to constant, where Q reversible is the amount of heat exchanged in the reversible process. Thus, we can say that the heat absorbed or lost isothermally and reversibly divided by the absolute temperature at which the heat is exchanged in a constant quantity for a given system. Equation 2 has been derived by taking positive sign for the heat absorbed Q2 and negative sign for the heat lost Q1. If Q2 is the heat absorbed and Q1 is the heat evolved, then Q1 by T1 plus Q2 by T2 is equal to 0. Summation of Q by T is equal to 0. Thus, when the isothermal and adiabatic processes in a Carnot cycle are carried out in infinitely small steps, the summation of Q by T terms equal to 0. Entropy is a state function. Consider a cycle process ABA. Carried out reversibly, it can be shown to consist a number of small Carnot cycles as shown in figure 4. The horizontal lines represent adiabatic processes while the slanting vertical lines represent isothermal processes. By making each Carnot cycle extremely small and increasing their number, it can be made to correspond to the continuous curve ABA. Thus, reversible cycle can be considered. Thus, the reversible cycle can be considered as being made up to an infinite number of Carnot cycles. For each of these cycles, we have summation of Q by T is equal to 0. When the changes are made in infinitely small amount, we can write summation of delta Q by T is equal to 0. For a cyclic process performed in two steps, that is from A to B and back to B to A, we can write that Q by T from A to B is equal to minus Q by T from B to A. It follows that Q by T is a definite quantity whose value depends only on initial state and the final state and is independent of the path followed for the system. For a reversible reaction, we can write quantity Q by T as Q reversible by T. Thus, we conclude that the quantity Q reversible by T represents a state function. This state function is called entropy of the system and is represented by S. Thus, S is equal to Q reversible by T. Entropy is an extensive variable and is defined only in terms of differences. The changes in the value of entropy is going from one state to another is independent of the path. Delta S is equal to SB minus SA is equal to Q reversible by T, where S and SB are the entropies in state A and B of the system respectively. As entropy is a state function, a small change in its value can be represented by exact differential ds. Hence, we can write ds is equal to Q reversible by T. Units of entropy. Entropy change is expressed as delta S is equal to Q reversible by T. Entropy is expressed in terms of joules per degree Kelvin. When the heat is expressed in calories, the entropy is reported as calories per degree. Further, entropy is an extensive property. It is therefore necessary to mention the amounts of substance involved. Usually, it is expressed for 1 mole of substance, hence the units of entropy are calories per degree per mole. When heat is measured in joules, we can write the units of entropy as joule per degree per mole. 5.08. Entropy change in a reversible process. Consider a process taking place under completely reversible conditions, that is, the system absorbs heat reversibly and the surrounding also transfers the heat reversibly. Let Q reversible be the heat absorbed reversibly by the system, and the heat lost by the surrounding will also be Q reversible. If the heat transfer takes place isothermally at the absolute temperature T1, then the entropy change in the reversible process will be the negative of entropy change of the surrounding, that is, delta S system is equal to minus delta S surrounding. Entropy change of the system is given by delta H system is equal to Q reversible by T. Entropy change of the surrounding is given by delta S surrounding is equal to minus Q reversible by T. The total entropy change for the combined system and surrounding will be given by delta S total is equal to 0. Thus, the following conclusions can be drawn from the above discussion. First, the total delta S for the system and the surrounding when reversible isothermal change occurs is 0. Second, the total entropy change for a reversible isothermal cycle is 0. 5.09. Entropy change in an irreversible process. If any part of the cyclic process is irreversible, the process as a whole becomes irreversible. Let Q irreversible be the heat lost by the surrounding. The amount of heat is absorbed by the system, but according to definition, the entropy change of the system depends only upon the heat absorbed reversibly. That is Q reversible. Thus, delta S system is equal to Q reversible by T. Further, assume that the surrounding lost Q irreversible amount of heat isothermally and in infinitely small step, then the entropy change of the system will be given by delta S surrounding is equal to minus Q irreversible by T. The net change of the entropy for system and surrounding combined is given by delta S system plus delta S surrounding is equal to Q reversible by T minus Q irreversible by T. Further, we know that the work done in a reversible process is maximum, that is, W reversible is more than W irreversible. First law of reversible process can be written as delta U is equal to Q reversible minus W reversible. When the same process is carried out irreversibly, we can write delta U is equal to Q irreversible minus W irreversible. As internal energy is a state function, delta U is same whether the process is carried out reversibly or irreversibly. From equation 2 and 3 we get Q reversible by T minus Q irreversible by T is more than 0. Comparing equation 1 and 4, we can write that delta S system plus delta S surrounding is more than 0. Thus, we can conclude that in irreversible process, the entropy of the system and the surrounding taken together always increases. All the processes in the nature occur spontaneously and all the spontaneous processes are thermodynamically irreversible. Thus, Clausius concluded that the entropy of the universe is increasing. The second law of thermodynamics may be stated as that is, all the spontaneous processes are accompanied by a net increase of entropy. That is, the entropy of the universe is increasing continuously. The results of the entropy change in a reversible process and in the irreversible processes may be written as delta S system plus delta S surroundings is equal to 0 for reversible process. Delta S system plus delta S surrounding is more than 0 for irreversible process. Combining these two expressions, delta S system plus delta S surrounding is more than or equal to 0, where equal to sign represents the reversible process and greater than sign represents the irreversible process. 5.10 Clausius inequality. The total entropy change for a system and surrounding for an irreversible process is written by delta S system plus delta S surrounding is more than 0. In Q irreversible is the heat transferred from surrounding to at temperature T, then delta S surrounding is equal to minus Q irreversible by T. Putting the value in equation 7, we get delta S system is more than Q irreversible by T. When the change in entropy is small, the above equation can be written as delta S ds system is more than Q irreversible by T. Expression 8 and 9 are known as Clausius inequality. Clausius assumed that the entire universe can be considered as an isolated system in which all naturally occurring processes are irreversible. On the basis of this, often stated as the energy of the universe is constant and the entropy of the universe always tends towards maximum. 5.11 Physical significance of entropy. The physical significance of entropy lies in its ability to provide a measure of degree of disorder or randomness of the system. The greater the randomness in the system, higher is the entropy. All the spontaneous processes such as diffusion of gases, flow of water down the hill, flow of heat from hotter to colder body are accompanied by increase in the disorder of the system. Thus, spontaneous processes are accompanied by increase of entropy as well as increase in the disorder of the system. It has been seen that melting of solid, vaporization of liquids are processes in which disorder has been increases and hence entropy also increases. We know that a solid having a definite crystalline structure has lowest disorder and thus represents a state of lowest entropy. The order is less in liquid and least in the gaseous state. Let us correlate entropy change with randomness by considering an entropy changes during phase transition. 5.12 Entropy changes during phase transitions. Change of phase in a physical process, it may occur in any of the following processes. First, a solid melts or when a liquid freezes. Second, a liquid vaporizes or a gas condenses. Third, a solid changes from one crystalline form to another. First, entropy of fusion or melting when a solid changes into liquid state at its melting point is known as fusion. Heat is absorbed during fusion. The entropy changes accompanying fusion is given by delta SF is equal to delta HF by TF, where delta HF is the latent heat of fusion and TF is the melting point of the solid. Second, entropy of vaporization. When the substance changes from liquid to vapor state irreversibly at its boiling point TB under a constant pressure, the amount of the heat absorbed is delta HV, that is latent heat of vaporization. Then the entropy change accompanying the process is delta SV is equal to delta HV by TB. It may be noted that both the processes, that is fusion and evaporation, are endothermic. Hence, delta H and delta V are both positive. That is, these processes are accompanied by increase of entropy. On the other hand, the change of the state from vapor to liquid or from liquid to solid involves evolution of heat and are negative. Hence, the processes of condensation of vapor and freezing of the liquid are accompanied by decreasing of entropy. Third, entropy of transition. When 1 mole of the substance undergoes change of state from one crystalline form to another, the entropy changes involved is known as entropy of transition. If delta H transition is the molar heat of transition of the substance and T is the transition temperature, then delta S transition is equal to delta H transition by T. As molar heat of transition, delta H transition may be the heat evolved or absorbed, thus the entropy of the transition may be negative or positive. Thank you.